Hi, I'm Steve Sklar. I'm here today to talk about data engineering at Predata. I am currently an engineer here at Predata. So first, I'm just going to give a brief introduction about who we are and what we do. Then I'll do the typical stack overview so you can see what technologies we're using. And then the meat of this presentation will be about task orchestration and how we run all of our things. So Predata is a predictive analytics company that collects and analyzes the structure of online conversations, and then we use these results to predict geopolitical, security, and market-moving events for a variety of clients, including some Fortune 500 companies. Now, I'm sure some of you have doubts about how social media activity can actually predict things that happen in the real world, but let me give you the canonical example of the Arab Spring. So there was actually a lot of run-up in increased levels of online activity before the Arab Spring, and this was basically a leading indicator. Now, if you are, let's say, like a hedge fund who is investing in oil markets, or if you are a corporate security department who has potentially assets in that region, or maybe even an intelligence agency, this could be a very useful information to you. Any type of predictive power that social media can show can actually be of some use to you. So we basically attempt to capture that using this example. There's the 99-1 rule, which is this famous rule, some of you may have heard of it, basically states that for any social media website, 90% of users are consumers of the information, 9% actually interact with the website. So they'll make a post or contribute to a discussion forum, and 1% of users are actually content creators, the power users who love to post pictures on Reddit and all that stuff. So what if we could capture what if there was some external factor that was actually causing some consumers to migrate to interactors or interactors to migrate to creators? And what could this possibly be? And could this even be something predictive like what happened in the Arab Spring? So how Predata works is users interact with each other on various social media websites, and these websites, like pretty much all of them, publish data through public and private APIs. We then collect information from those APIs and turn those into time series signals. And we then feed those time series signals into predictive models and descriptive models as well that give us a concise view of the type of online activity that we're attempting to track. And one thing that I would like to make note of is that Predata is not an NLP company, so we're actually not looking at any of the textual content of these of this activity. Basically, what we're trying to do is just measure we're attempting to quantify the conversation. So we're looking at the size or how argumentative the participants are, which gives us a few advantages. First of all, we're language agnostic since we're only looking at numbers. And also it helps us to avoid some privacy concerns because nobody wants to get involved with that these days. So now I'm going to give a little talk about our engineering stack as I play with my notes. Okay. So, like probably a lot of you, we're Python shop. Our machine learning stack is your typical Pandas, NumPy, scikit-learn, all that stuff. We use PostgreSQL hosted on RDS, on AWS, and in fact, pretty much all of our infrastructure is hosted on AWS. We use Celery and RabbitMQ for task orchestration, which I'll go into later. And on the web side, we use Django. We make heavy use of the Django ORM. We also use the Django REST framework to talk to our front end, where we use Mithril, pretty cool if you haven't heard of it. We use D3 for our data visualizations and all that other fun stuff. We use Docker for deployments. We use Elastic Beanstalk, although we are looking to move off that into something similar to Terraform in the near future. So now for the fun stuff, task orchestration. So first, let me give a little introduction about our data. So our universe begins on January 1st, 2010. This is the point where we decided that there was really enough online activity for us to be able to start making predictions on anything really. So if you think about that, we have one observation per day. Now some sources may actually have more granularity than that, but in order to keep everything consistent throughout various types of sources, we decided to make one observation per day in our time series. So you have from January 1st, 2010 to today, July 11th, that's around 3,100 maximum observations per time series. Now, for those of you dealing with time series data, you may realize that that's actually not a lot of data points, as some of these series can reach the hundreds of thousands or potentially even millions or greater size. However, what makes our data very interesting is that we can collect potentially millions of these series as we collect more and more sources and throw them into our system. So, okay, so celery. A lot of people here maybe use celery, but if you haven't, I'll give a brief little introduction. So celery is basically a Python library that lets you run tasks remotely or locally. It's pretty easy to use. All you need to do is you have a function, in this case, create user, that accepts 2 args. You wrap that in a special task decorator, and now you can run that function locally just by calling it normally, or you can run it remotely, as I do below there, by calling .delay. You can also use .apply async, pass a bunch of different options in terms of how you want to run this, and what will happen is, oops, wrong slide. Okay, well, what will happen is Celery will basically send that information to another worker to run, and I'll have more detail on that, not in this slide, but in the next one. So, Celery Canvas is a very powerful thing that really is the core of what makes Celery so powerful. Basically, all it is a bunch of special tasks that allow you to link together your existing tasks. So there are 3 main types of special tasks in Celery Canvas. The first is a chain. And what a chain does is it basically just acts as a pipeline. So it prevents one task from running until its parent has completed. And what's actually very cool about these is you can pass data from the parent to the child, just similar to a Unix pipe. So you can build up pretty sizable chains of tasks. Then you have a group, which basically allows you to run a bunch of tasks asynchronously in parallel. That's cool, but if you need to synchronize it, that actually turns your group into a chord. So what that'll do is basically your chord head or your group of parallel tasks will all execute. Then Celery will actually hold the chord body from executing until the chord head has finished. We use these a lot, and in combination of chains, groups, and chords, you can run a lot of different things, and we like it a lot. So now kind of going back to what I was saying earlier, how Celery actually works is you have a function that calls .delay, and this function then sends a message to a RabbitMQ exchange, generally RabbitMQ exchange, that contains information on the task that you want to run and any args and kwargs that you need to run that task. In the default configuration, that exchange is simply named Celery. So that message then moves along that exchange across the Celery binding to a queue also called Celery. Here you have workers, other machines that are basically watching this queue. As a message then hits it, the worker will retrieve it, deserialize it, actually run the work, and then save the result in a storage layer, which is generally Redis, and that's probably the best supported one and the one that we use. And there, you can either have your initial task blocking for this whole thing to happen, and it can either pick up your task, it can either pick up the result then, or it can do a bunch of other stuff, and either that thread or another thread or really any type of process can pick that up off of Redis and continue processing. So Celery also has a lot of built-in routing things. So they have basically something called a routing function. This is different than anything inside of your message broker like RabbitMQ, where basically it is a function that accepts, again, your Celery task and any args and kwargs, and it will return a dict that says which exchange to route this message to and which routing key to use. So with this, you have very fine-grained control over which exchange and queue you want your message to land on. So you can do cool things like this, where right now we have two exchanges. One exchange accepts a bunch of messages from our web app, and the other one for our nightly pipeline. Now remember, I said our data points are basically, our data granularity is 1 per day. So we have a big nightly pipeline to process all that daily data. Now, let's say you're a user and you are adding a source that requires some processing while our nightly pipeline is happening. In the default configuration, what will happen is you have this one Celery queue with thousands of tasks on your nightly, from your nightly jobs, and your message gets to the very end of the queue. So you have to wait until this large batch of potentially really expensive jobs runs for your work to be complete. But with the new Celery routing, what we're able to do is actually route that message to another exchange, the app exchange, which then allows you to route the message to different queues that you have completely different workers listening on, so your work gets done hopefully instantaneously, but maybe a lot shorter than it would take if it was on the nightly queue. So that was my Celery part. Now we're going to talk about Luigi. There we go. So Luigi is basically allows you to build trees of dependencies. Now, not to be confused with Celery tasks, Luigi tasks are basically, they're, how can I describe this? They're basically, they're tasks, but the way that Luigi works is you have, you basically write all your tasks and their dependencies in code. So for each task, what you'll do is you'll say, task A depends on task B, which depends on task C, and so on and so forth. You build up this massive tree of dependencies. And what's cool about Luigi is it comes with a built-in visualizer like this. So you can visualize all your dependencies. Now, we use Luigi in interesting ways. Probably how it wasn't designed for, because we actually don't do that much work inside our Luigi tasks. Instead, what we do is we basically run a Luigi task that runs a Django management command. Okay, there we go. Runs a Django management command. And so what happens is then that management command actually launches thousands of Celery tasks that hit our nightly queue. So they're routed by our RabbitMQ nightly exchange to the proper queues. Workers pick it up and they're chugging along. The Luigi task will then write to AWS S3 saying, hey, my job is done. At that point, it basically, your Celery work is running asynchronously and Luigi continues to evaluate the tree. But what happens if, since we're not doing that much work in your Luigi tree, how do we know that your work is actually completed if it's running a bunch of asynchronous work through Celery? So there's this cool thing, basically, well, it's not that cool, it's just the RabbitMQ. It's just the RabbitMQ, thing. So, yeah, so basically what we do is we take a look at, we send each task. Let's say we're running, I'll use an example. Let's say we're running a process to process all of our Wikipedia page views. So what we'll do is we'll run a management command that says update all Wikipedia. That will then, due to our routing rules from our Celery routers, actually send all of the Celery messages to our update Wikipedia queue. So we can now monitor the update Wikipedia queue and wait until all the ready and unact, which in this case means basically still working jobs, to be completed. So we keep on basically every 10 minutes checking the queue with this thing. We basically run through there. If there are still messages in the queue, we raise an exception, and then we wait 10 minutes and try it again. And the reason we have to do this is because Luigi assumes that you're actually doing work inside the task. When in fact, you're actually, since we're doing work asynchronously, if a Luigi task, here's something interesting for our Luigi friends, if a Luigi task runs but does not raise an error, Luigi will automatically move on to the next task. And that's really bad for us because we have a bunch of async work running, so then it'll run your next task, you'll have more async work that depends on the previous async work, and then you end up with just like a giant mess, and it's horrible. So the way that we do it is we just raise an exception. And yeah. And then eventually the queue is empty, and we don't raise an exception, and Luigi moves on to the next job. So hopefully that gave you a kind of big picture of what we do, and what are we doing to improve this, since we're always looking to improve things at Predata and probably everywhere. So Dask is the big one that we were looking at. So Dask is basically another way of running asynchronous work on a bunch of machines. And we've played a lot around. We played around a lot with it, and we really like it. We think that, or I think that it is it basically allows us to do all of this work that I described in one line of code. And the problems that we have with Dask are that it's really difficult to import Django models. We do use the ORM heavily, and that is a big restriction for us. And then also, there was one other thing, but I forgot it. So yeah, but we are going to look more into Dask, and if you have any experience with Dask, or if you find any of these problems challenging, and you like this stuff, which I'm guessing everybody here does, we're hiring. Surprise. So that's it. Any questions?
Hi. Why did you guys opt to use Luigi and your kind of homegrown Celery system instead of using something like Airflow and kind of just leveraging like the Celery executor in there and doing everything in like tasks like that?
Yeah, that's a great question. So we really liked Luigi's not the execution model, but we liked how we were able to define tasks in code. I agree that it's definitely not the most efficient solution, but at the time, I personally had I came into the company with more experience with Luigi, and that was one problem that we were running into, which was basically, at that point, we had a much different and less robust task framework. So honestly, that's the reason why we chose it. It's definitely something to look into. I find something with a lot of these task frameworks, they come in and out of favor, so it's really hard to kind of ride the right train, and we may or may not have. It's yet to be seen.
I have just few questions, but they are very small. What version of Celery is in production? Is your RabbitMQ clustered? And the third one, how many tasks a second do you have?
So we are using, what are we? We're using Celery, I think we're using Celery 4.1. And sorry, what were the other questions?
Is your RabbitMQ clustered or just like a single instance?
It's a single instance on Cloud AMQP.
Okay, and how many tasks in second do you have?
In Celery, we have probably hundreds of thousands, if not millions.
In 1 second?
Oh, in a second. Oh,
yeah.
no.
Sorry.
That would be awesome. It's difficult to say because we hit it all at once when we run a management command. So there's like a lot of throughput right in the beginning, and then it kind of slows as we're chugging along on those processes. We haven't really come close to hitting any RabbitMQ or to RabbitMQ limits. So, any other questions?
Thank you.
All right, thank you.